Welcome to my tutorial on automated parameter tuning. I'm going to mostly focus on heuristic search, as the subtitle says. And I'll first, though, answer the question, what is tuning all about anyway, so that we're all on the same page here. And for this, I typically like to use this model of a black box. So this is how a black box looks like. And the inside of the black box could be anything that you want to tune. So you want to tune a certain device that you have. I typically have algorithms that I want to tune. You might have a circuit that you want to optimize, so some machine. And you give certain parameters to the device, the algorithm, you need to set certain settings, and then out you get a certain performance, so that you can hopefully measure somehow how cool it is that you set the parameters in a certain way. So I'm actually a mathematician. I abstract away from this what's concretely beneath this black box. Just say it's any black box. I can ask it questions in the sense that some parameters come in and some performance comes out that I can measure somehow. And so since this is now pretty abstract, let me first go one step back and make it one step more concrete again. So as one example, if I have some kind of microchip, say, then this microchip might have certain kind of voltages or as parameters under which it needs to work. It has a certain layout. The wiring is made in a certain way. It has a certain temperature at which it's supposed to operate. Maybe even a pressure. I don't even know what kind of parameters might one want to adjust for or improve or just try to see what is best. Either way, you get out some kind of behavior of this microchip. So for example, the speed at which I can run it without it doing nonsense, right? Maybe the energy it consumes differs depending on what I set the parameters to be. Maybe the reliability is different. Maybe the lifetime changes. Maybe it makes a different kind of faults. Anyway, so all these kind of things are performance parameters or performance measures. And the microchip's parameters are on the left side, the voltages, layout, temperature, and pressure. So you can imagine any setting that you want. It doesn't really matter so much. Whatever it is that has some parameters that you want to tune, that you want to check, and you have some performance measures on the other side, that now is tuning as I want to understand it in this context. So back to the abstraction. So by the way, I'm actually a mathematician more than a computer scientist. So I'm usually abstracting away a lot of things. So for me, the input is just some bunch of numbers, typically real numbers. It doesn't even matter so much. If you prefer complex numbers, if you only want positive numbers, if you only want 0 and 1, that's what computer scientists sometimes like to do. So instead of all real numbers, it just takes 0 or 1, yes or no. You can mix those even. So you have some kind of input vector and out. Let me focus for now on just one single measurement. I will talk later a little bit on what's happening if you actually have many objectives here, not just one performance measure, but many. That's a special topic I will touch on later. So for now, let's suppose we have just one thing that we want to optimize. We have a lot of variables to play with, and one thing should be as good as possible, basically. Now, basically what this boils down to is tuning is the optimization of functions that have this shape. So you have r to the n and you map it to r. And this is what tuning is. You want to optimize this function. Now, what does optimize mean? It means you want to find a maximum or a minimum, depending on how your problem is phrased. So the maximum speeds at the minimum energy consumption, or yeah, it doesn't make a big difference whether you maximize or minimize. It's typically interchangeable. And I will just talk all the time about optimization, and whether you want to maximize or minimize is up to you. So now the question is, what can we do? We have this huge parameter space, right? It's uncountably infinite. And I have some kind of performance that I get for anything. And what I can do is, well, this is this black box setting. I can guess some parameters, let's say, and I can read off the performance. So if I have an algorithm, I can pick some parameters. I can let the algorithm run and see what is the performance. If I have a chip, then I can, well, try out something, try a layout, temperature, pressure, whatever. And then I can see, is this good or is this not so good? So, and this is the setting that I want to talk about now. I will later come a little bit to looking into this black box, because, well, we sometimes know a little bit of what's in there, but especially in this abstract computer science stance, it's sometimes good to say, let's assume I don't know anything about what's in there. I just know that I can plug values in and I can get a measurement out. What can I do? And already then I can do quite a lot, being completely agnostic about the backgrounds or the inside of this black box. And that's what I want to talk about first, and then we talk a little bit about what if we can take a peek into this black box. So how would you even start about this? So you have to guess some kind of first initial number. Maybe you say, okay, I know I don't have arbitrary numbers. My numbers are in a certain range between 0 and 2 or some bounded range. Still, there are uncountably infinitely many possible settings that I can run. And I'm still wondering, how can I have the best final result? And now it depends a little bit on the so-called landscape. So how does it look like? If, for example, we have such a landscape, then we say, okay, there seems to be a peak somewhere at roughly the origin, 0, 0. Doesn't need to be there, could be anywhere. But whenever I start at some kind of maybe random point or some kind of selected point, somewhere here on the surface, then you would say that, okay, this point itself might not be so good. I want to optimize. I want to have the top point. How can I get there? What can my algorithm do to find it? And then the typical first idea, first approach, then this is hill climbing. So hill climbing means exactly that. You kind of want to go up, 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 up. And that's a local search. So local search means you are somewhere, and then you look around you at all kinds of neighbors, and when you find a neighbor that's better, then you go that way. So you go up. Now, how far around you should you look? So for example, should you look in all possible directions? Should you only look into the cardinal directions? Should you go at step size of 1 or 1/2 or 1/4? Now, there are different ways of handling this, of adjusting the step size if it's too large, adjusting the step size if it's too small. Excuse me. So the local search hill climbing has certain techniques that it uses in order to figure these things out. I will talk a little bit more on this later, but for now, let's just assume I can always look a bit around where I am and then see. So I'm just probing the black box. How about this point? How about this? How about this? How about this? And then, well, I find better ones, and whenever I find a better one, I go there. And then I look around this new point, and then I go up, look around this new point, up, and so forth. This is hill climbing. It's a very basic, straightforward algorithm to find improving moves, and then hopefully I will end up in some kind of global optimum. And that basically brings us to the first problem that we have with this very simple algorithm. what happens if it's not quite so easy. For example, if we have such a surface, then as you can see here, there are two local optima. So we have one smaller peak where one would say, well, this is not such a great solution. There's a much better at the top peak. But once this local search climbed up to the small peak, it will never figure out that there's something better around. It just looks around in its local vicinity and be like, best thing I can find. So it will just stay there, hang out, and be like, okay, I guess I'm done now, and leave it to you to take this and go away. And that's, of course, not always quite optimal. So the question is, what can one do now? It's in this case rather easy. The objective function is such that it's actually, if you start with a random point, more likely to be in the top peak because more points kind of lead to it than at the lesser local optimum. So what you can do is you do random restarts. So you start your hill climbing algorithm, you go up to some peak and be like, okay, it looks fine here. I guess I don't get any further. Let me have another try and let's see whether I end up somewhere else. If you have a deterministic starting point and a deterministic procedure of where to go, of course, everything will end out exactly the same way. If your fitness function, if your objective is deterministic, but you just have to randomly do certain things, randomly do the steps, randomly start at the random points between, well, a random tuple 0, 5 and 0, 5 or whatever. I should maybe mention, so maybe in my computer sciencey thinking, this was clear to me, but maybe I should mention that anyway. So the height of the point here indicates quality that we measure, and the X and Y coordinates, they are basically my input parameters. So X and Y are the inputs, and then out I get the quality measure. So this is why I want to have this maximum. Yeah, so now with random restarts, we can already get a bit further down the road. We can already achieve a little bit more. And this is particularly useful if, well, the probability that you start somewhere nice is high enough, then you don't need to do it too often. And in general, this kind of local search and just running into your optimum around you, this is pretty well understood. There are many good algorithms to do this. And for this just kind of vanilla search, you can already be successful rather easily. Now, the search is typically a bit more complicated than that, and you might know that from your own work, especially also if you work in machine learning, as I understand quite some of you do. It's not that easy. So sometimes the landscape, and this is now minimization, so I'm trying to get into some kind of valley point here. Sometimes the landscape is very rugged. So you have many local optima, and just by restarting, you just land in a different local optimum wherever you are. And basically, wherever you start, you're almost immediately in a local optimum. And it's just no way to get out of this just by hill climbing. There are various ways to get out of this. These are so-called search heuristics that just try out something, some heuristic procedure to kind of get out of local optima. They are frequently nature inspired, it's called, meaning that you have some inspiration from some kind of natural process, biology, physics, chemistry. Do I know something from chemistry? I don't know. And you model an algorithm after this. So for example, you could take the physical annealing process and have so-called simulated annealing. And that means that you sometimes want to also leave local optima. You're pretending your metal is still hot. Stuff can still wiggle around a bit. And you do try to hill climb whenever you find something better. That's cool. If you find something worse, then maybe you will accept it anyway, just because it might get you out of a local optimum. This has been tried a lot. In my personal opinion, it's not the smartest thing you can do. There are many other options that are a bit more focused on finding the optimum, but the simulated annealing is already much better than plain vanilla local optimization, hill climbing. Other things that you can do is, for example, derive inspiration from biology, in particular evolutionary and genetic algorithms come here in play, and you have a certain population is typically then where you have many solutions at the same time, and you try to interpolate between as well. That's called crossover, or have some worse ones die out, some better ones continue, and then see how you can move through the search space, not just with one point, kind of trying to find a minimum, but with many points. So this is something that that I in particular do some research on. And if we now talk about this interpolation, so how can you imagine that? So with this crossover, you're trying to really get something new and kind of to get the best of both worlds. Imagine you have like two solutions to a problem. One is good in this area, one is good in that area, and you kind of want to combine it. That's really what crossover is. So to tell it in the words of a story, imagine you have a Pocahontas and you think that's a cool story, but really you like more science fiction. Then you might come up with Avatar in the end and be like, okay, it's the story of Pocahontas, but in a science fiction setting. So it's the best of both worlds, maybe, if you like that. So this is what crossover is. And this has been used as an inspiration by computer scientists to say, okay, I have two solutions, the purple one and the yellow one. And now I'm mixing them up randomly a little bit, and I get some yellow purple things and I get some purple yellow things. And what good do they do? Well, maybe the points at which they were crossing over are such that one of these solutions has the best of both worlds, and then the other thing has the worst of both worlds. Maybe. So you can again throw them into your black box one after the other and see, oh, this one's shitty, away with it. Ah, this one is super great. It's better than either of the parents. Let me keep it. Yeah. So this is the idea. And this whole language of parents and offspring and population and so forth. So this is all borrowed from biology, and it's just a way of being a bit cute, I would have to say. So that computer scientists can talk about these algorithms a bit more easily by reference to nature. But they are very precisely defined for the algorithms. And via this inspiration, they actually have pretty good results. Anyway, so as I said, we take evolution somehow as inspiration. And what happens then is that we sample new solutions somehow in the surrounding area. That's called mutation. So mutation just is you have a solution, you modify it a little bit. You can imagine that just like local search, it is typically characterized as being not necessarily local. So a mutation can also mutate at a lot of different parameters, can change a lot of different parameters in a lot of ways, even strongly. So that would still be considered mutation, while local search typically stays in one place and basically only wiggles one of the parameters and just a little bit. So mutation is then the term, again, taken from biology. And then you pick good offspring, and that's called selection, again, from biology, just to make things easier to talk about. And if you have crossover, then this is just one more way of sampling new solutions. and then you kind of cross over again. So how does that look now in terms of how do the things optimize? So for example, you might want to find this very bright spot, and you have some kind of population that is sampled according to some distribution that is kind of indicated by this ellipse here. And then you evaluate them all, so all 20 or 30 of them, of these points, you throw into your black box and be like, so how good are they? And then you see that, okay, the ones closer to this white light are better, the ones further away are worse. And now what you do is, okay, you change the ellipse with which you want to sample. You say, oh, more this way, more this way. And then you sample in this area. And then you basically run down this gradient, and then you see that, oh, whoops, now I'm running past my optimum. So my ellipse is already covering much more than just this small part that's bright. And then you say, okay, let me focus my search. And then you draw in and you get closer and closer. And then you basically find your optimum this way. And you can home in and now do some fine tuning, right? So basically you automatically, or I mean, this algorithm automatically adapts its step size so that it can later do the fine tuning. In the beginning, it made big steps. It might even decide to make the ellipse even bigger, as we have seen from generation 1 to generation 2. Yet more words borrowed from biology. With the generation, and then it contracts again towards generation 6. So this algorithm that I've shown you here that does exactly this is the so-called CMAES, the Covariance Matrix Adaptation Evolutionary Strategy. It's a pretty famous algorithm. You can get implementations in a lot of different programming languages. You can use it to tune anything you want pretty much. It will mostly focus on the nearest local optimum where you initialized. So you need to be a bit careful where you started, but with some restarting tricks and so forth, you can also avoid this a little bit. And other than that, it's very fast, it's very good. It can deal with ragged landscapes thanks to its sampling approach. It can also deal with all kinds of other problems that I'll talk about a little bit in a minute. Anyway, so whenever you have some kind of problem like this, you really have real numbers and you're just trying to find the optimum, then CMAES could be something worth looking at. So here we are. So there are numerous other approaches that you can take. So for example, one of my favorites, and it's been mentioned in my introduction, is taking ants as an inspiration. So ants are kind of running around from the nest N to the food source F and trying out different paths. And ants communicate by putting on the ground certain pheromones. So I guess now that's the example from chemistry, maybe. And the other ants can smell these pheromones and thus see, oh, here was an ant that carried food. And now it's not just one ant that does it, it's many ants. And the ones that take a shorter route will be able to put down more pheromones, basically because, well, the route was shorter. And then ants are more likely to follow this path and reinforce this path even further so that in the end, all the ants will be traveling this shortest path. So this is what biologists actually found out in the lab, for example, and saw that, yeah, ants can solve computational problems this way in some kind of distributed manner, which is why it's called a swarm algorithm or swarm intelligence. So people now, computer scientists, have taken inspiration from these ants and decided to term it ant colony optimization algorithms. and actually developed some algorithms that's doing quite well on a number of problems. For example, where you need to find things like paths, but it's also been translated into various other settings. The term swarm optimization actually encompasses a lot more. For example, the bee colony optimization algorithm, or the particle swarm optimization, which takes inspiration from flocks of birds. Some of them make more sense, some of them make less sense. It's always a bit funny. You see me smiling. This algorithm for the ants is actually a real and a good example. There are a lot of examples where people have just thought, okay, which animal didn't have its own algorithm yet, and let's make up something. So not all of that stuff makes sense. For this one, I mean, there was a major book by Marco Dorigo and Thomas Stützler, respectable members of the community. They have detailed this approach and analyzed this approach. So this is one of the ones that is more thoroughly analyzed and has its true merits, and others are just sometimes knockoffs of known algorithms, or just rephrasings of known algorithms. And it's not always so scientific necessarily. Anyway, let's focus on the good stuff. What else is there? Many of you, especially when you are a computer scientist coming from hyperparameter tuning and machine learning, you have probably dealt a bit more with brute force searches. And this is also kind of what might have come to your mind if you tried in a physics lab to optimize something. So you have some kind of grid search, for example, where you want to try all kinds of combinations. So you just have some parameters x1 and x2 between 0 and 1. And then, well, you just pick possible values for x1 and x2, and you try all combinations. And then you already see a certain landscape coming out of this. Similar but different is random search. Just, well, I can just pick some uniformly at random from this space that should also give me a certain coverage. And of course, I can also combine these things a little bit and say, okay, I make some kind of methodical search, but I'm gonna focus on good areas once I found them, for example. So in general, these kind of approaches are pretty good for getting some kind of initial feel for the landscape, getting through a little bit, identifying values that are promising, and then maybe use this as starting values for something else, or refine this approach. There are many refinements of these approaches. I'm just kind of skimming over the surface here for you so that you get a feel for what's out there. Once you want to apply this, then maybe there are some more specialized approaches that really focus now on good areas. Yeah. It's also good for an exploration because you have a good coverage of everything, right? As I said before, if you have more these local search algorithms, they quickly focus on what's going on here. And so they don't explore so much, they exploit the knowledge that is already there. So this is then called the exploration versus exploitation trade-off. Do you want to exploit what you already know, what you found out so far, and kind of be quick, get some, or do you want to explore? Do you want to spend your time, your precious evaluations in particular, to find something better? So one word on the cost metric here, typically for optimizers. So if I want to optimize something, I can do all kinds of computations in the background. They are typically fast and don't matter. What matters is how much does it cost to throw something into the black box just once? Does the black box give me an answer after milliseconds, microseconds? Or does it say, I'll tell you tomorrow? If it takes until tomorrow, then I just have to see, okay, maybe I can have just a few days of computation until I want to be done. Maybe I can parallelize on a huge machine or something like this. So if I want to try out an algorithm, I have a cluster of 1000 cores and I run the algorithm 1000 times on different inputs. Then I can make this grid very nicely and easily and get them all done within one run, even if each run takes overnight. But of course, then the cluster of computing cores is busy for the night, right? So I do pay, but it's nicely parallelizable. While this local search gets typically away with a lot less in terms of um, uh, waste on exploration, let's say, but then homes on one point and you can't really parallelize it. You have to kind of go step by step better. What you can, of course, do is you say, well, I look at many points in the neighborhood at once and then pick the best. So these are some strategies by which you can parallelize and maybe improve a bit faster. Not every time you want to optimize something that you can run on a computer. Sometimes you want to optimize, say, a drug that you want to administer to patients. You give the drugs to patients, they run a clinical trial or stuff like that. And then after a few days, you might get back initial results. Maybe it's a half-year long trial before you can change things again. Obviously, if one iteration takes you half a year, that's a bit too long for the search techniques we have here. Then you just talk to your medicine professional and see how they currently do it. But if it's a bit faster than this, then typically you can already use some of these approaches, which are all designed to bring down the number of black box calls, of number of times you want to poke this fitness function, your quality measure. This is really always the goal. Now, one caveat for this, no, it's not a caveat. So if you have a badly behaved landscape, so it's not really local so much, it's jumping around. The summer here is good, there's bad right next to it, and it's just jumping around, then such a grid search is a very good possibility to just get an overview, because any kind of local search, any kind of population just will be stuck wherever you are in that corner of the search space. And with the grid search, you really open up and you explore. And if you have a badly behaved landscape that doesn't help you, then you can just do everything in parallel, because whatever you knew, whatever you learned about the search space previously doesn't help you anyway, because it's so badly behaved. That's what I mean by badly behaved. Previous knowledge doesn't help you later. Anyway, then kind of this brute force is all you can do anyway. Okay, so when we are now doing this kind of searching, what are the problems that we deal with? So maybe a bit in summary, we deal with this ruggedness we've talked about, we deal with local optima, but we can also deal with other things like noise. Let's say if I throw in parameter once into the black box and I measure, and then I throw in the exact same parameters again and I measure, and out I get something else. That's what I would call noise in general. So there are certain algorithms that can deal with that better, some worse. Some might just say sample 20 times, take the mean, something like this. Typically, the algorithms we employ are more efficient than if you first bring down the variance of your noise. They can kind of handle quite some variance all by themselves. You don't have to bring it down too much, to bring it down some. There are also algorithms that can deal with dynamic changes. What do I mean by dynamic changes? I mean that this kind of black box, the thing that you want to optimize, doesn't stay in place. It kind of changes its internal wiring. But these are always very exceptional settings and not so easy to handle, but there are a number of algorithms that can deal with that. In that same topic is also re-optimization. Re-optimization means I already found a good parameter setting for over here, and now I have something else. Now there's something else is different than before. I have a slightly different black box. What can I take from my previous search to the new search? And this also is part of this area of dynamic changes, of re-optimization. And there are certain techniques that one can use for that. Stagnation is another problem that needs to be dealt with. So you might get closer and closer to some optimum, and you always make tiny, tiny improvements, and it's not really getting anywhere, but it's getting better and better. So the question is, when do you want to call it a day and say, okay, I'm done now. I want to make a restart. I want to look more broadly. I want to just deliver my result and say, here, that's it. That's as good as it gets. So there are various heuristics for dealing with that as well. Then we have some practical considerations. I already talked about evaluations being very costly sometimes. So this is where you need to have an eye on. And this in particular happens when you have some kind of hardware in the loop. So for example, you might want to evolve a robot. You might want to teach it how to use its limbs, how to walk or something. You can have a so-called surrogate model. So you're not optimizing the robot itself, you're optimizing a model of the robot. And once you have optimized this model, you just deploy this best parameter setting onto your robot and you say, hey, now you can walk. Typically turns out it cannot because your model wasn't good enough. The model needs to be pretty good for this to work, and you typically don't have such a good model. So hardware in the loop means, well, you don't ask the surrogate model for how good your parameter setting is. You ask the robot. You say, hey, run. And you're like, oh, you fell down, but you made it at least a little bit. Okay, let me put you back up, preferably in an automated manner. Otherwise, you can't run overnight without PhD students suffering too much. And then you will really optimize the robot and not just some model of the robot. And then you can even combine these two approaches. You have the robot run a little bit. You use this to refine your model. Then you ask your model, okay, so what would be a better way of moving then if this is how you move? So you are kind of optimizing your model then a little bit, not too much. Then you let this run on your robot again. Your robot will fail again. You will learn something about the model of the robot. You improve your model of the robot. You optimize your model of the robot again, and so on. So in this interplay with the surrogate models, you can sometimes save some evaluation time for the robot. It's probably very costly to let the robot actually walk and tumble and fall, while the surrogate model you can probably optimize in a matter of seconds. So you can kind of squeeze in a bit more knowledge about your robot with this surrogate model. Another practical consideration that computer scientists like to forget about after they optimize the hell out of something is that just having a super good result, this parameter setting leads this result, and super cool, is that the solution typically needs robustness. If you deploy something in the real world, if you're actually going to use something and not just run an algorithm, then whatever you set the parameters to be, they're not going to be exactly like this. They're going to be slightly different. You can't set the temperature super precisely. There will be some kind of range. Same for all kinds of other parameters. And you sometimes want to deal with this in the sense that you say, I don't just want a good parameter. I want a good parameter that is also, when I wiggle the parameters a little bit, they're still good. So this is some kind of robustness. There are other notions of robustness as well that can be used. And in this direction, I want to show you this little antenna. So this is one of the early successes of evolutionary computation, where this antenna was designed with the help of an evolutionary optimizer. I think this is by NASA. So they have the luxury of deploying their little antenna at 0G and no air resistance and what have you, so that I guess the robustness doesn't need to be as high as when I put it on my roof and there's wind and rain and what have you. But then maybe it also needs to go through the strain of getting out of the atmosphere. So maybe there is some robustness needed. Anyway, so this was one of the early success stories where the engineers have said, I don't know why this antenna is good. It does weird things. It goes weird angles, strange shapes. Somehow it works really well. No one knows why. The computer tried it, it works. So now I need to, sorry for that. Anyway, so this antenna was designed with the help of evolutionary algorithms. Now I promised you to touch a little bit on multi-objective optimization. So multi-objective optimization means I still have the same input values, but I care for not just one performance metric, but for many, and they are typically competing. Otherwise it wouldn't be fun. So I could optimize the one and then it's super bad in the other. So let's say I want a really fast car. Well, sure, I can get a really fast car. It's going to be expensive though. Or I want a really cheap car. Well, it's not going to be fast. So I want some kind of trade-off, but I don't really know which. I want something that's fast and cheap or something of that sort. Maybe something that uses just little energy in some kind of microchip while being still very fast to do my computations or some such. I have a number of choices of how to deal with this problem. So for starters, I can just, these are the YI, these are the performance metrics. So I have D different performance metrics. I can just take a weighted sum. So I pick the weights, they kind of normalize everything and they say, this is so important, this is so important, and this is rather unimportant, but if I can improve there, then I take that too. Now this is just one single objective, the sum. So I brought this entire vector down to a single scalar, so it's a scalarization. I don't need to do it with a sum, I can do it any way I want. I have some kind of function that takes the arguments and gives me just one scalar in the end. It's the easiest way so that you can say, yes, I have a lot of performance metrics, but in the end, I can tell you how I value them, and that's what I want to get out. So I once was part of an industry project where we did this for some company that basically then tried to put euro values on everything. So if I get a little bit more here, that's worth €2. If I get a little bit more here, that's worth just €1. So this sum is then the overall reward or what that I want to maximize. But I can also go other ways, more intrinsically multi-objective ways, and return multiple candidate solutions. Be like, here, how about the BMW? It's not as costly as a Jaguar, but also still nicely, maybe fast enough. And maybe give some trade-offs and be like, if you want to be any faster, it's getting more expensive quickly. If you want to be any slower, you don't even save so much money. So some kind of sweet spots and maybe some multiple candidates. In the extremes, in the most extreme case of multiple candidates, you have a trade-off curve where you say that, okay, so from you can have something over here and then all the way to there. So you give kind of optimal trade-offs for everything in terms of speed and cost, but you don't give any options where some other option is better in terms of speed and price. That was the two dimensions I had. Yeah. So these are basically the options you have there for dealing with multi-objective optimization. Now, a good question is, why do I want to have these heuristics at all? So I've been talking all this time about this heuristic search, was kind of also in the title of this tutorial. So why do I want not just the best, the algorithm that does it all? Why a heuristic? For this, I have the following quote for you. So a heuristic is an algorithm in a clown suit. It's less predictable. You don't really know what's going to happen. It's more fun, certainly, with these kind of evolutionary computation buzzwords and colony swarm intelligence and so forth. And it comes without a 30-day money-back guarantee. So you really don't know what the heuristic will give you in the end. It is typically very easy to deploy. It's very cheap to develop in that sense. It typically gives decent results, and it's most of the time extensible in the sense that if you put in some more time, the result will be better. But you already have some kind of result that is already good, and you can put in more time until you like the result. Once you're done, once you say, okay, the result is good enough, you can stop optimizing your optimizer. That leads me now for the last 10 minutes to a quick overview of some special cases. So what if we had more information and not just a black box? So maybe we have a gray box. We know a little bit about what's going on in our box. We don't really know the details, but we can, for example, know derivatives. What if we even have a white box? What if we know the precise problem statement and are not just looking for the optimum? So as the first example, for the gray box, we have gradient descent. So gradient descent means, so you have the optimum somewhere sitting here in the middle, and you start somewhere, and then you're like, okay, so which way is down? In which direction does it improve? And then you just go in that direction with some small steps. So you compute the derivative, and then you go towards the optimum. So if you can compute a derivative, that's the gray box part, right? If you know something like this, then just do that. It points towards the optimum. So just go. That's a variant of Newton's method that can go even faster, and that now requires even more derivatives. So it's even harder to do and harder to estimate. But in fact, the CMAES is also a variant of this kind of gradient descent method, just that it doesn't need to actually do the derivative. It's kind of estimating the derivative. Okay, so that's what I wanted to say about the gray box. Now I have some more white box stuff. So this is so-called linear optimization. So you have here two vectors, and you have the vector-vector multiplication. So you basically have the sum, the weighted sum of all your variables, and you have some kind of constraint that, well, you have some matrix. You have some kind of linear constraint. Some sums should be at most something. And maybe all your vectors are supposed to be non-negative. So this is the most general case of, well, some general case of linear optimization. And it's actually a very important optimization theme, since you can press so many other optimization problems kind of to look like this, or a variant of this. So a number of variants of this have been analyzed as well. There's a lot of research on this. If your problem looks anywhere near like this, optimize this sum conditional to these kind of constraints, then you get this kind of solver, and it can probably do magic stuff very quickly. Can deal with vectors that are very large. I don't know what the current number is of number of variables you can deal with in this sense. But anyway, so if your optimization problem looks like one of those, then you can consider it solved. And the same is true for many other very particular special cases. So within computer science, I talked about the general black box setting where I don't know anything about my search space and I still want to make progress. And I believe that this is an important case for all of you or for many of you. But there are some special cases. If your result looks anywhere near like a special case, then just translate it into the special case and use a solver off the shelf. That's even more true for a number of algorithmics applications. So sometimes you want to find structures. Round tour through all the capitals of the states, what do you call continental states of the US or what? You can find an optimal such tour leading to the shortest total distance traveled. With brute force, it takes really long, but there are very good algorithms for doing that reliably, efficiently, any way you want, basically, that give you such a round tour. And if you have a problem that looks anywhere remotely like this, then you just want to translate it into such a problem. So these are now, what, 50 states, 50 cities that you want to connect. 49, anyway. You can go up to 1,000 cities that you want to connect, or 10,000, and the algorithms will still be able to deal with this. So if you just want to have some points, we followed. If you don't want a round tour, if you just want a path or something like this, it's all kind of the same. There are all kinds of specialized algorithms that do exactly this problem solving. Yeah, so the heuristics that I talked about in the beginning, they can do anything badly. Now here there are algorithms that can do only one thing very well. So this is the trade-off here. Depending on whether you have one of these something that can be done very well, then you're done. Otherwise, you need to resort to a heuristic. This is one more example. It's called the minimum spanning tree. You find this green structure here inside of this overall structure. With lowest total edge cost while everything is still connected. Is a very classic example from computer science where there's a very fast algorithm that just deals with it and is done with it. Checking certain formulas, be it numeric or logic formulas like this one, is a very famous example, again, from computer science that is practically solved. Where if you can somehow squeeze your problem into this, and I've seen a lot of exciting problems that don't look anywhere near like this, be squeezed into this kind of form, and then you just throw a solver on that can deal with 100,000 variables or some such, and then after one night's computation says, here, done, this is the optimum. Here you go, thanks. So there the algorithms are very advanced and can basically do what you want. The caveat is it typically needs an expert to kind of squeeze everything into this formulation, and while typically also takes a lot of time even for this expert to come up with this thing, so it's not like in an instant easy to see. It's a tailored approach. You can't really do that for every problem that comes to hand, so this is why the heuristics are so important. Right. So with my last few minutes, I'll just want to give you a short conclusion. So we looked at this black box setting with a single parameter performance, but I also talked a bit about this multi-criteria approaches, and we looked into the two cardinal directions of heuristics on the one hand and other more white boxy approaches, gradient descent as a gray box approach on the other. So with this, I want to thank you all for your time.
Thank you very much, Timo. Thanks a lot for the super interesting tutorial. There is already a question. I invite, first of all, everybody that has questions to post them here on the Q&A. There is already a question by Natalia Ares. She's asking, thank you for your awesome tutorial. Is there any hope for optimization landscapes that are mainly flat and it has just a thin, tall peak?
Yeah, the simple answer is no. If you don't really know where this thin, tall peak is. So this is called the needle in the haystack problem. And with this black box approach, you can't do much. So what we find is that frequently this flat surface is sometimes a bit artificial, in the sense that whoever defined the problem said, this is a bad solution, it's bad, zero, bad. You could instead say, this is very bad, while this is only a little very bad. And this is, yeah, bad, but not very bad. So if you can have some kind of quality assigned to bad solutions that you don't really want at all, then you can guide the search towards where you want to be. This is not always possible. So basically, it happens a lot when you want to find an initial feasible solution. So sometimes your solution space is so highly constrained, you can't even ask your black box for certain values, or for most values. You ask it this value and it says, no, my machine will explode, or something like this, right? So in this case, yeah, you need to find the first feasible solution with some other means. So this is actually not a rare thing. So yes, Natalia, I understand this problem very well. There is no general approach to this.
So if nobody else has if while we wait for other questions to come out, I have a question that is somewhat related to this point that Natalia raised and you just answered. And the question I have is, can we define like a class of problems for which, for example, this swarm optimization or ant-colony optimization algorithm that you were mentioning, for which they are good at finding solution? Yeah. And in what way, for example, this definition of this class of problems is related to the shape of the landscape of the objective function you're trying to optimize?
Yeah, so this can be done, or rather it can be done in the sense that you define a class of fitness function, of objective functions, and then you can show that a certain algorithm is good on this function. This is basically my bread and butter. This is what I prove, frequently. And so far, I mean, when it comes down to really proving stuff, it's fairly limited. If I tell you these problem classes, you'll be like, well, this is a boring problem class. It's tiny and can't do much. And the optimum is obvious to begin with, or some such. But it gives us some initial feel for what these algorithms can do. Let me tell you the easiest and most well understood function class. So the fitness is just the distance to the optimum. So I hide some optimum somewhere. I don't tell you which one, and I say, okay, the quality of your solution is just the distance in some kind of norm or metric or whatever space. So that means that you can just now do local search, and you find something that's closer, and you find something closer until you found it, and then you say, well, distance 0, I found it, great, I'm done. So for this case, it's actually well understood how does the proof, how does the search progress, what are the strengths and weaknesses of the different algorithms to do this. So for these kind of very simple landscapes, it's pretty well understood what is happening. There are also some other landscapes that are similarly well understood, but not so many yet. So if you really ask for guarantees, so this is the clown again, right? You don't get any guarantee from a heuristic. As a theoretician, it's my business to give guarantees, kind of, to prove something this will hold for sure. And I can do that in a few cases.
Thank you very much. Thank you for your answer. Like, if there are no other questions, I will. Okay, sorry, my Siri is going crazy. Sorry about that. If there are no other questions, like I would ask you like probably a stupid question. Like, oh no, there are maybe. I saw that there are other two open questions. Sorry, I will go first about these questions. So Evert van Nieuwburg is asking saying great tutorial and overview. Thank you. Could you elaborate a bit more on what the standard ways of including hard approximate constraints in optimization problems are, e.g. when using CMA ES?
Yeah. So so especially for hard constraints, for the CMA, yes, there are different constraint handling techniques that you mostly want to start somewhere. So you typically like hard constraints so that you know, okay, it's somewhere in this box. So if you really can give some constraints, then you can say, okay, it needs to be somewhere in this box. So I sample my initial solution inside this box, and that's good. Other constraints are a bit harder to deal with. So what you can do whenever you have these kind of approaches that kind of want to probe the black box, you can now kind of make an outside black box around your inside black box and say, whenever I get something outside of bounds, I will return some value that will indicate that this is a bad region. And that kind of tells me how far away am I from the good region. So this is what I meant earlier when I said, but just by saying this point is bad 0, I'm not helping the algorithm. I'm helping the algorithm when I say this point is 5 away from any good area, then the algorithm will know, okay, so this is a bad point, but it's 5 away. So if I find a point that is only 3 away, it's better. So this is one way of incorporating that. So having a soft boundary. There are other ways of dealing with it. So always projecting a point that's outside of the boundary kind of onto the boundary. This has disadvantages. It, for starters, confuses the algorithm typically, which is not always bad. The algorithms deal with confusion. I mean, evolution is a very confused process to begin with. But yeah, there are a number of ways to deal with constraints. If it's really all about constraints and the insight doesn't matter, then it's more of a constraint optimization problem. Then the other techniques are more important. But if it's just some kind of, well, stay inside this box and otherwise do your search, then there are a few of these constraint handling techniques.
Thank you, Timo. Also, for everybody, remember that there is the Slack channel. So if you want to, I'm copying and pasting all the questions over there. So if you want to continue the discussion and ask more clarification to Timo, also you can do that over there. And there is another question by Natalia. She's asking, for the experimentalists in the audience, can you expand on techniques to fight noise and hysteresis in measurements?
So I actually don't know what hysteresis is.
Okay, maybe what we can do for Natalia, we can actually promote her and join the conversation. Can you just 1 second? Now
I special. I have a special route. Thank you so much, Timo, and that was a fantastic tutorial. Yeah, so you mentioned a bit about this, that when you have noise, of course, well, you know, one technique is to, for example, evaluate many times and make an average. sometimes what we and other dynamics of the landscape, of the optimization landscape. Hysteresis in particular is when you sweep in one direction and you sweep in the opposite direction, and you get imagine that there is some quantity that changes. It might, at the threshold, might be one in one direction and a different one in another. I don't know if I'm explaining this clearly enough.
So you are somewhere?
Basically.
And you go in one direction and then your performance value changes?
Yes. And then it changes back. So it can be in two states, let's say, and fluctuate a bit.
So if I can add on this, maybe it's like in a non-Markovian process. So where the state does not depend only on the previous position, but it depends on where you're coming from.
Okay, so basically what you're saying, if I ask the black box once for one point and then I asked it for another point, what I asked it previously influences my question. Ooh, I have not considered this problem before. This is pretty annoying. Yes, so that would probably call for a very specific way of handling this. So I can tell you for noise, so these population-based approaches that ask many questions anyway, they don't ask the same question many times. They ask different questions many times, and then they can see where the gradient is kind of taking them. So when you talk now, so I mean, for noise, it's kind of smoothed out. For hysteresis, that's an interesting problem. I'm guessing that these algorithms, these heuristics, are not so bad at dealing with it if it's not so strong, because a lot of questions are asked, and then so there are more like the white box algorithms. They say, if you say this number, then I'm going 100% and trust you on this, and this is what I take, and this you should not do in this setting, right? So these evolutionary algorithms kind of by default don't trust you. So they are like, okay, you might say this looks good. I'll be a bit hesitant and search anyway. So they are a bit careful by default, which they pay for in terms of speed, how quickly they get where they need to go. I would be thinking that they are somewhat fast at getting there anyway, because of the way they approach the search. So the short answer to your question is I don't know, because I've never dealt with such a case, but I'm hopeful that it would work, and I would think that a specialized approach could even work even better.
Perfect. Thank you, Timo.
So if there are no other questions, I think we could thanks again, Timo, for your really cool tutorial. And I would like to invite you all to the next session. That will be the poster session in 20 minutes. So we have 20 minutes break.